I'm excited to tell you a little bit about the research that we've been doing in my lab, and I just want to preface this is a lot of collaborative work with many other faculty and students, so I don't want you to think that's all me, right? This is on some of the work we did a couple years ago was this idea of exploring underground spaces with a team of drones, wheeled robots, quadrupeds to autonomously explore this, find objects, and that really started motivating a lot of our research in these very degraded environments, right? So here the drones have to be, for example, fully autonomous because you don't have communication with your base station, or only intermittent communication because of rocks in the way. And so the system has to be really resilient. And so you can see here also the environments that it has to fly in are very different, right? So there's these big open spaces, some very narrow spaces. So here's a part of the cave that we were flying in, and then you get to some more urban situation, and the system has to work without any changes in these situations. So you can kind of see it lining up with the doors. This is inside a cavern, so you have to be able to handle dust. And so these are some of the challenges that we are excited about. And so if you think about this, really has to go beyond just kind of a demo, right? Here you really have to have something that works for these challenges. And so there's a different set of trade-offs that you have to make, right? So and we'll kind of look at this a little more, when you see research a lot right now, it's very focused on performance. That often leads to some brittleness in the approach, right? So here you really want to be more on the robust side than the performance side. So everything's done on board here. So the system is building that map, creating plans on the fly. Everything's on board, and then it's detecting these objects. So this is inside a steam boiler plant. Then let's see, this is inside this was inside a former nuclear power plant. This is inside a coal mine. So you can see in Pittsburgh we have lots of interesting testing locations. Some of these are also tourist sites you can get to. So this coal mine, cavern, also sites you can visit. This is inside a former veterans hospital. So these are some of the test sites that we used in this challenge. And so you can also see that if you think about the algorithms, there are different challenges here. So here's one of the corridors. You can see it's very featureless. So if you're doing LiDAR-based SLAM, right, that will not necessarily be happy. The drones have to coordinate with each other. So here is inside a limestone mine. You can also see some of the degradation and also the type of environments that we're excited about, right? So here the two drones coordinating inside the mine. And so maybe let's move on. So and so one of the things that we think about is like, how do we think about resiliency for these systems, right? So we want these systems to be resilient so that we can deploy them in a lot of use cases. And so you can think about resiliency as robustness, redundancy, and resourcefulness. Those are characteristics of your system. And you can also try and measure potentials for resilient performance. And so these are not a property of the system, but you can define them as a performance of the system you can measure. And so this is an area of engineering also called resilience engineering, if you're more interested in the kind of keyword of what to look for. But I think there's, some of these are not easy to measure, right? It's often much easier to measure performance, but I think it's something for us to, it's worth it for us to think about is like, what will it take to have these resilient systems? So in this space, we look at different applications. We have these teams of drones that gather information, look at wildfire mapping with drones, off-trail driving, aerial manipulation, and operations in shared airspace. And so in this work in sub-T, we had this very, I would say, traditional handcrafted setup, right, where we go in, we have a good SLAM system, mapping, planning, and put that together, and it worked quite well. But these handcrafted representations are still pretty vulnerable, and they're not necessarily robust enough for resilient autonomy. And so how do we represent the world in a way that allows us to do resilient autonomy, and how can we exploit cameras to their full potential? So we are interested in trying to shrink these drones down to a very small form factor, maybe just a single camera. And so how do we push perception along those lines? So in this talk, I'll focus more on the left side here, on the perception side. And then we do care a lot about the planning part. If you're interested, you can look at more of our work on the right side as well. But today I'll focus more on the left side. So I'll start with going back to basics and talking more about basic perception, mapping, planning, and kind of some new takes that we have on this. And then think about perception, representation that we can use for this autonomy, and then show some other small highlights, some fun videos that we can maybe talk about. So one motivation that we have is we want to move to, you can think about it like the single V1 for robotics, right? So right now, each objective often has their own model for a task. You might have some object detector, some SLAM, some VLA. Everybody wants to do their thing, right? And so that just does not work if you actually want to have a robot that can do something, right? You're going to run out of GPU, you're going to run out of what you can do, right? So can we have, process a pixel only once and use it for many tasks? So that's one of the approaches that we're excited about. And so the question is, can we build this kind of one encoder that can give us many different outputs that we can then use to build an intelligent system? And so some initial work along this direction that we have looked at is called MapAnything. The idea is that we can have one model that can do 3D reconstruction, but also you can give it different inputs, and then you can get a metric reconstruction from this. And you can take calibration, non-calibration, depth maps, not depth maps, and so on. And so if there's one model, you can do different tasks. You can do monocular depth, you can do SFM, depth completion, localization. So you can complete many different tasks from this. And so here's just some results. So you give it just this video, and you can get many different outputs. And you can imagine that those outputs are quite useful if you want to have an autonomous robot. And since it's is monocular, you can also try and run this on many different drones that only take a single camera. Here's just some other fun videos. I'll just play this here. So you can, so the question is, there's several questions here, right? So one of these is, how do we, in the future will be, how do we scale this to longer horizons, right? So right now there's a limit on how many images you can take, and then how do we combine this with some other sensor inputs better? So there's a lot of future work in this area as well. But before we get there, just kind of to put this work a little bit into context. So there was some prior work called Duster, that one of the downsides is that you have to predict multiple DPT heads. There's also another work called VGGT that's quite popular. And so Downside here is that you have to do redundant predictions, and you can't really model arbitrary cameras and camera models, and you don't have flexible inputs. So in our approach, we have a factorized output. So we have a single DPT head that has multiple outputs. We predict a scale, and then these ray directions you can think about as the equivalent of a camera model. So it supports an arbitrary camera model, but basically a camera calibration comes through these rays. Additionally, you can also give it different inputs. So you can give it rays as input, which is a camera. If you have a calibrated camera, you can give it a calibrated camera. You can also give it poses if you already have those poses, and just use it for depth completion and depths. Now, one of the keys to really make these types of models work well is actually really good data, right? So you want to have very precise depth maps and poses. A lot of the data is actually synthetic, because you can really get good 3D reconstructions and poses for this. And so putting this all together, you can get a nice model. You can try this by yourself. There's some Hugging Face demo. You can just upload a video, play with it. It's pretty easy. Here's a quick comparison with visual inertial odometry. So this is using an off-the-shelf stereo visual inertial odometry there's a ZX, is a camera manufacturer, but it comes with an odometry, so we figured it's a good baseline. And it is on that camera, and then on the right is MapAnything, but only using monocular images instead of stereo. And we clipped it to the same depth range here, just to be kind of a fairer comparison. And so if you look at the drift of the kind of ZX visual inertial odometry just compared to that model, you can see that you actually get much less drift. Independent of us, people have actually used this model now also on some robot use cases, and it has turned out to be quite useful. So this is not our work, but somebody just used the model. The model is also reasonably fast, so it can, with 2 images, it can run at, 15, 16 hertz maybe, and so it's actually quite a useful model. Now, once you have this model, and the next question is, could we extend this to 4D? So one of the things that we're looking at is, can we use this for scene flow estimation, right? And so that's useful, especially if we want to have better simulators, do collision avoidance, or anything related to people as well. But to do scene flow, we need camera poses, geometry, and then also to predict the scene flow, right? So which is a lot of the tasks that MapAnything already does. So here, what we do is we take the MapAnything architecture and extend it with this scene flow head, and also add an input for Doppler for radar inputs, right? So imagine you had some radar that can give you some depth flow, so you can also add that to your system. And so with this, we can get good results, and you can look at the details in the paper. And so these are some of the kind of qualitative results on some of the scene flow estimates. And so this uses this MapAnything architecture, extending it to 4D. And so high level, the idea here is, can we extend, can we use this system to build a unified front end for many different tasks, right? And the first step here is a lot on the geometry, right? So you saw your depth estimation, pose estimation, and so on. The next step will be adding more of the semantics to this, and then you have a unified system. Just a little teaser. This is kind of coming out, but recently we've done some work to also speed up this estimation of things like MapAnything and VGTT by a factor of 7 to 10x by not estimating not useful areas. So that will come out soon. Okay, so visual is nice, right? But as you saw in the previous video, there are many cases where just having visual data will not be sufficient, right? If you're flying inside a dust cloud or at night, you need some other sensor inputs. And so we've been looking at extending a lot of these methods to thermal as well. Now, thermal cameras are nice because you can see in situations that are very challenging for visual cameras, because you're measuring, in this case we're looking at long wave infrared cameras. And but you can't just use a thermal camera off the shelf, right? So you have to really map the representation of thermal cameras. So here we're training a new backbone called AnyThermal, which is, if you do that and align it with the visual backbone, basically all of your visual approaches will still apply for the thermal. So what do? If you recall, in the MapAnything approach, we use Dyno V2 as kind of the front end input. We align the thermal images to match the visual Dyno V2, right? So now, if you align the thermal, AnyThermal, which is essentially Dyno V2 fine-tuned on thermal data with the visual representation, now you have a unified space where you can use all the existing methods, right? So it's the same backbone. And so now you don't need to fine-tune like for visual place recognition, segmentation, or any of the other tasks. You can just use the regular front ends. Now, but the key problem is really that thermal data sets right now are not sufficient. And so there are some data sets out there, but the key is really to get good data. And so last year at ICRA, there was also a thermal workshop, and one of the things that came out of it is that, we should get together and come up with a platform that can simplify data collection for this. And so we came up with this open source platform that incorporates a ZX camera, a stereo thermal camera, and Orin AGX and battery, and most important, a button. And so I don't know how many of you are working in field robotics, but we have a kind of hard rule in the lab that no typing in the field. Of course, the weather for you is too nice, so you don't have freezing hands or something like this when you're out in the field. But buttons are important. So that's just a rule. Anyway, so we use this sensor payload to collect a tartan RGBT data set. And so the key here is really that we have hard synchronized thermal and visual data across a wide range of environment. And we'd be excited to have more people kind of contribute to this to get a wide range of data sets, because one of the limitations, as we kind of show in the paper, is really how much data you have. Really, as you add more and more data, the system performs better, which tells us that we just need to get more data and more variety of data. What are we doing next? So we're adding radar to this, as well as a LiDAR, to just have kind of a full setup. And then that really gives you a way to get kind of all aligned data time synced in a nice little package. So And we talked about resilience a lot, so thermal is one way to do this. Another way to do this is to really try and leverage the IMU as best as possible, right? So here, we are purposefully degrading the LiDAR so that there's no measurements from the LiDAR, right? And so, but we still want to be able to estimate well. So this is showing a run across the campus at CMU at night. And so now you know what happens at CMU in the middle of the night. And so here we kind of purposefully make it very hard for LiDAR sensors. For example, we go out into the middle of the field, we go down narrow staircases and featureless hallways and so on. And so we want to be able to have good odometry in all of these situations. And so this is kind of a 40-minute run. And we get a very small kind of endpoint area, and the map stays aligned. And the key here is that we learn an IMU model on the fly. So we rely, if the LiDAR is available, we rely on it a lot. But once, while we're doing that, we are refining an IMU model that was pre-trained on a lot of data. And then if we are degraded, the system relies more on the IMU alone. So, so that is kind of one of the other techniques and areas that are quite exciting, is to think about how can we get the maximum out of these IMUs, because you cannot jam an IMU. So, so this gives you an idea. So this is odometry, no loop closure. So, there's been a lot of work, and people are very focused on pinhole cameras right now, right? Because it's very easy to get this. Your phone makes pinhole images, but actually, fisheye cameras are becoming much more popular in many use cases. So you can think about, augmented reality VR glasses. Can be for data collection for humanoid, or if you're on a drone, you want to be able to see in any direction. But deep learning models right now do not handle fisheye images very well, because the distortion changes across the image, right? So in the center, for example, the pixels will be aligned. As you move out, things basically start distorting. And so you can create virtual pinhole images, but that adds more computation and complexity. So one of the things we've looked at is how do we extend this idea to spherical images. And even you can also think about, if you have a set of pinhole images, if you just project them into a sphere, you can basically do the inference purely in that spherical space. And so what we do is we project the images into this canonical spherical space and then come up with a different ways of doing convolution in that spherical space. So, yes?
Very good question. So, do you need to know the camera model for each image?
In this case, yes.
Okay.
So in the previous MapAnything, it estimates a camera model. Here, it is assumed it's a calibrated intrinsic calibration. And so you take the image, you project it into this sphere, and then you do a resampling to get this a uniform distribution, and then you have different ways of doing the convolution. So I'll talk a little bit more about each, the spherical convolution and spherical pooling, and we implemented those and trained those as well. So there are different types of how you can do this sampling to get a uniform resolution, right? If you've ever kind of taken one of these 360 images, there's like different compression and distortion as you do this. So you want to get an even spread so that your performance of the model is the same everywhere. And these different sampling strategies have different trade-offs. And then you can implement the spherical convolution, And you can also, you have different design choices there as well, depending on what you want to get out of that spherical convolution, right? So if you, for example, look at only the distance, it becomes rotation equivariant. If you add in the angle, then you get different features out of this, right? And so it depends on what you want to get out of your network. And so this gives you some idea of how you can then resample this, right? So these are always a little tricky to visualize because you're essentially taking that fisheye image, then you have it in that spherical space, and then you're reprojecting it into this canonical sphere. And so with this type of method, now you have a way of having this single spherical image that you can do a lot of the operations in. Right? And so there's still more work to do, but the idea would be that now you can take all the previous work and extend it to these wide field of view cameras, and that would really help you increase efficiency, right? So if you have let's say a drone, right? Ideally you want to have a very wide field of view because you have to go up, down, you really want to exploit the 3D nature of this system and not have a bunch of pinhole cameras. Something else that's kind of a core feature is to be able to do matching, right? So matching, Takeo Kanade used to say, right, what's the most important thing in vision? Correspondence, 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 right? And so the idea is, okay, how do we unify wide baseline matching and optical flow in one method? And so we want to be able to have something that's precise, but can also do wide baseline matching. And so we came up with this method called UFM. And again, this is trying to use the same input space to have this kind of unified input. And so this gives you some idea of, imagine you're trying to match one image to the next, right? So this can be big viewpoint changes or smaller viewpoint changes. And you can see the image 0 projected into image 1 or image 1 projected into image 0. The architecture, again, is we have this Dyno V2 input and then have self-attention. And a core feature to really make this work well is to have this co-visibility because you don't want to learn things that are not, where you don't really have any information. So that's kind of a key to make this really work. I'll skip some of the data set parts, but just to kind of give you some idea. So we're basically matching from one image to the other, right? So this is just an image transformed from one pixel to the other. There's nothing fancy or nothing being made up. It's just transforming one image to the other. Similarly here, so you have two camera images. One is that ego camera, and the other one is a static camera, and it's just matching the ego camera to the static camera. Right, so just a pixel by pixel matching. And so you can see that once you have that type of dense correspondence, that's kind of foundation for a lot of vision tasks. If it's estimation or mapping and so on. Localization. Here, just a couple of other videos. And again, you can also play with this if you have some interest. Okay, cool. Now, in this UFM basically gives us a good way to do this matching. And so now, last year we developed this method called, yes? Sure.
I saw a lot of people sent you a video for information, but this is just only for map purpose, or you will also use this to somehow change the direction.
So this is purely a vision task here, right? So this guy is wearing these glasses, and so that's the video you're seeing here. And there's a static camera, and we're just showing, okay, if you have a pixel here, if you have a pixel, let's say, here, where would that match in this image? So it's purely image matching, nothing fancy happening. But I mean, this forms the foundation for a lot of tasks on top, right? So you could imagine, let's say you want to do manipulation from image to image, flow could be very useful. So one of the use cases, how we can use this matching, as an example, is in the visual odometry method that we developed. It's called MacVio. So it's a stereo visual odometry method, and the key for that method is really that it leverages the uncertainty estimation well. So having good uncertainty estimation can really help you select the right key points, and then you can do better estimation. Now, in the original method, we had the original method used a different backbone, and so for that, the uncertainty estimates were good. So here we had to work a little bit more on integrating that with UFM, with this other method. But if you do that, we can get some very nice odometry outputs. And this is just showing some example on a Kitty data set. Okay, cool. Now, so we talked a lot about perception, and maybe I can take a kind of quick clarification break here before we get into more the action piece. Any questions? Yep.
Sorry, would you mind re-clarifying what were the limitations of VGGT and so what motivated MapAnything?
So there are a couple of things. One is speed, and you have multiple prediction heads, and the other part is you can't give it auxiliary inputs, right? So we wanted a way to, let's say we have a calibrated camera, you want to be able to leverage that, or if you have a depth map or poses, you want to be able to give that to our model, and it should perform better. Okay, so once we have this, visual input, right now there's a lot of work on saying, okay, let's learn a policy end to end in terms of mapping this to outputs. You can think about this as kind of type 1 decision making, right? So this is stochastic gradient descent, problem solved. But if you think about what's kind of happening in general is you want to be able to have the option of choosing, having a sense of memory or mapping, and then having a way of trading off between different choices, right? And so if you think about this as your higher level planning, then the question is, if doing that all the time is not very efficient, right? So then you can think about this reflexive decision making more as compression, right? You're really trying to gain efficiency. So if you just have type 1, you're really kind of skipping a step here. And then the other question is, how do you go from this reasoning back to improve your model? And we'll kind of skip that part, but if you're interested, we can talk later about this. So once we have this kind of nice input, we want to be able to do long-range semantic reasoning and plan for this. But one of the challenges is that if you're doing this semantic navigation in an indoor space, often it doesn't really matter what you do because your space is so small, you're going to find what you're looking for anyway, right? So you don't really have to be very intelligent. But if you're on a drone, you see very far. And so you want to be able to exploit that knowledge, but you will not have depth at that point. So the idea was, can we build a representation that combines both the depth mapping as well as this kind of more directional mapping? And so that's when we developed this representation called RayFronts, which basically has this 3D semantic map in addition to these ray-based vectors that give us the long-range mapping. And so we want to be able to have both for our reasoning. So for example, if you have something like a water tower, you will not have that in your depth map, but you want to be able to get the direction to move towards that water tower. And so we built this 3D semantic map, and then at the frontier points, we store the ray directions of certain things. So just to kind of give you an idea of what this looks like in real time, So we build that map on board of the robot. So we have the semantic voxels, we have the occupancy map, and then we have the frontiers. And then based on these frontiers, we have these rays. So you can see these various semantic rays. And then, so this is the representation that we're basically building on board. And this is kind of an open set representation. So you can give it different queries. So ground, road cracks, and various radio tower. And here you can see that this is pointing outside of the map, right? Because it's storing these rays. And so that gives you a very rich representation to start reasoning over. And so then we can combine this with some of the navigation. And so this is some initial work that just tries to start to leverage these types of representation. And so here, really, we're doing this kind of visual language navigation. So we're saying, hey, I'm trying to find the water tower or something like this. If you see it, you're trying to, you can just go to it directly. If you can't see it, then you have to think about, okay, how do I, what should I do next to get there? And that's where some of the LVLM comes in. And so we use that RayFronts representation as this kind of task agnostic memory. And I'll kind of skip some of this in the interest of time. But we can, so for example, if you already see a house, we want to find houses or ships, we can just go there. If it's beyond the sensor range, we can go towards the rays, right? So here's no water tower in the 3D map, but we can see it in the distance. And then if we don't see it at all, we basically fall back to an LVLM. And then we've also tried this in real time on board of the robot without the LVLM. And so, one of the things, so this is just kind of a high-level idea of where we're trying to get to. There's still a lot of work to do there. But one of the things I wanted to come back to is, we want to be able to have these resilient robots. And so one of the things we need is to have data sets that really push the limits of what's possible, right? And so we've been usually also part of what we do is create a lot of these data sets that might be useful for your research. So like Tartan Air, Tartan Drive, aviation, and Amelia is the largest open data set of aircraft movement in the US. Here's one other data set setup that we have called Map It Anywhere that also tries to, for example, use some existing data to create these useful representations that you can use for sidewalk navigation. So we try to push the envelope on a lot of things, and I'll just want to show you kind of a couple of fun videos, some of the other work that we've been doing. So this is, for example, detect and avoid. So we have detecting aircraft on board, and then have a kind of CBF-based policy that avoids other drones. We've tested this with this is the drone on here. That's doing it's also doing GPS denied localization. But so we run this detection on board and then avoid the drones. And we had closure rates of up to 136 kilometers an hour. And the own drone flies at 36 kilometers an hour. Let's see. So one other area that might be fun is this idea of general purpose aerial manipulation. So this is an area that we've looked at quite a bit. And so the approach that we take there is to really think about an end effector poles as the main control interface. And so we have this drone that's a fully actuated hexacopter with an arm on top. And then we have this end effector centric whole body control. And then we have two ways of operating there. So one is to have human teleoperation, and we can use that as data samples to learn a policy. So just to kind of give you an idea, this is just showing some of the end effector centric control, right? So we're trying to control the position of the end effector, and the body basically follows this. And then you can do things like do this teleoperation, and then and so the question is, how do we do this? And I think this might be familiar to you, this picture, right? So the question is, how do we take these demonstrations and move them? I'll kind of skip this. How do we move this to a drone setup, right? And so the question here is, one of the limitations is that what you see as the observation is not necessarily executable by the robot. And so the idea is to use how well the MPC works to improve the diffusion policy that you can use for manipulation. And then you can do some things like this fruit picking, for example. Just a little example. And then, so, oops, yeah, I'll just, in the interest of time, always fun to see. And one of the other parts of this is that this is, since this is a flying system, right? This is not like tabletop manipulation where you have a static setup, right? The whole system's constantly moving. So you need your policy also to be robust to this. Some other things that we look at is, for example, off-road driving, autonomous off-road driving, and off-trail off-road driving. So the approach that we are taking there is to not try to label data by hand, because it's really hard to say, hey, is this a dangerous rock? Is this, what is dangerous, what is not dangerous? So the way we do this is by imitation learning and then self-supervised learning. So as the system executes, it experiences some things, and we use that to improve the system on the fly. So it's building that 3D voxel map. Those are basically the same foundation models, features that I showed you, and then we use those features to learn a cost map. And so then one of the other things we can do is do that at night without LiDAR, just using thermal cameras. And one of the tricky parts is field testing in this situation, because you can't actually see where you're going. So actually, the students look at the laptop screen. But yeah, we have to be very careful in these experiments. But then, so what we're doing here, you can see again, we're essentially creating those same aligned features that I showed you before, and can actually map them to consistent costs for this off-road navigation. And then we can use, since we have this stereo thermal data, we can also use that to do stereothermal odometry, so to create these maps at night without any active illumination. Before I finish off, I just want to give you a quick kind of idea of where we're going next and what's kind of motivating us right now. We're currently doing another DARPA challenge. It's called the DARPA Triage Challenge. And the idea there is really to have this team of robots that assess people in a mass casualty situation. So you can imagine some kind of disaster. And before even first responders get there, you have to decide, hey, who do I go to first? Which priority do I visit them? And it's a very time-critical situation. These are all simulated, just to kind of preface. This is not real, so we have to do that at night without visible lights and during the day. And so you can imagine, a lot of the stuff I talked about, there's very similar challenges here, right? Like, how do you see at night? How do you make sure you can localize people? How do you assess them? And so on. And so just to kind of summarize, so our approach is to create a unified perception system and use that for this decision making, right? We want it to be economical and on board, ideally. And to really have these good autonomous system, you need good representations. And as a theme, we like to work on these like impactful problems and really try and make them work. I think that's a lot of, we like to kind of do this more mission-driven research, I would say. And so that's kind of very exciting for us. I just wanted to kind of end with something maybe that makes some discussion, opens up some discussion. And so, I think there's a lot of talk about world models right now, but I think we have to think about really like task-conditioned world models, right? The reason we build these models is to solve a task, right? Like there is no one universal world model, right? The only real world model is the world itself. Every abstraction is wrong, right? And so these world models need to be economic, right? They need to make our task easier to solve. So, really think about like what will the model be used for when you do this, right? If you think about a lot of the work right now, the objective is to reconstruct, visually reconstruct the same scene that you saw, or create a visually appealing scene, right? But that's not necessarily what you need for, can be nice for simulation, but it's not necessarily what you need for onboard robot navigation, right? And what that abstraction is depends, right? If you think about just an object, right? If I think about my laptop, maybe an object is my laptop. If I want to remove my hard drive, I probably need to model the screws and each piece of that laptop to be able to take it apart, right? So it really depends on what your task is, what your representation needs to be. So just something to think about, maybe some ideas. Okay, cool. Thanks, everybody.
We have time for a couple of questions.
Yeah, thank you for the talk. I'd be curious to hear a bit more about how you trained the arm on the drone. Like, is there a manipulation policy and a path planning?
So it's
and then,
right. So the architecture you can see a little bit here. Right. So the idea is we have these teleoperation demonstrations, and then it's just an ACT, training that policy. The other, so that's one approach. The other approach is this, having this more general diffusion policy and then refining it based on the MPC. And the data for that one comes from this, these demonstrations, right? These human demonstrations. So those are the two paradigms.
I'm curious if you have any thoughts on like what is the right representation for 3D geometry? Like for MapAnything, do you think it's just like an input to like a voxel representation or stuff like this?
Right. So I think there's a progression that we're going through. So for now, this RayFronts type representation is very explicit, a very explicit voxel representation, and I think we can do a lot with that. There are some questions after that. Hey, can we build a more implicit representation that's deeper in the system where we don't have this explicit mapping? I think that is definitely an open question that we're also excited about exploring. Yeah.
So like thermal data are you expecting that is required to make systems like as capable as for like RTP vision? And do you think there's like some potential that RTP images can be transferred into thermal images and we have then like liquid synthetic simulators for those?
Right, so we tried, let me kind of go back to the thermal maybe. So we tried to do some of the style transfer and so on. It works okay, but in the end, you do need. I think a good way is to get more data, even just to validate some of the style transfer. or learn how to do it, right? I think that, but you need ideally a bigger range of temperatures also, and thermal contrast at different times of the night, and I think we need a lot more data. I don't know, the other part of it is the quality of the thermal cameras, and different cameras might have slightly different noise patterns as well, which is a little bit of an open question. But I mean, the data we have right now is not a lot, and we're seeing the performance is already reasonable, right? Like we can do, for example, for the off-road driving, right? We can actually transfer the style and still, get reasonable features. And so it is not, for now, I think we're not seeing like a drop-off. Like we don't know where the fall-off is yet.
Do you think this works because we have already done all the training on RGB and we reuse basically all this knowledge?
Right. But I mean, we are fine-tuning the whole. Backbone, the whole. So, I think it will need more than what we have. Yeah. But yeah, I mean, maybe it's not that far away from the RGB, not so far away from RGB that it still works okay.
Have you run into any limitations on how big you can generate on hardware? Like how much land you can cover before the maps themselves just become too unwieldy?
Right. So so there's a couple of things here. So for RayFronts uses an underlying map representation that's based on OpenVDB, which is kind of you can think about it like a shallower octree, right? So it basically has maybe 2 levels, and then it initializes some chunks. So it's relatively efficient, but it is the features. It also depends on what you store as the features in each voxel. So if you store the raw dyno features, then it's going to get pretty big. If you do some dimensionality reduction, you can store more. So that's kind of the limitation there. For MapAnything, there's a certain, the performance drops off, as you add more and more. Let me see if I can show this real quick, right? As you add more. Oh, where's it? Okay. So as you add more images, right, your computation increases, but you don't necessarily have to. Feed it all the images, right? You can just chunk and restart, which is what that result that I showed at the end does, right? So I think this is only using one or a couple images and then basically using it more like an odometry. Yeah.
Can you talk a little more about the imagery management when it comes to integrating solutions and robotic applications, apart from more efficient? What other practical measures where your team is forward, and are there any questions that are worth looking into?
So you mean in terms of energy energy efficiency for things like inference and so on?
Like drone flying in the cave,
Right. Yeah. So, and there's some interesting questions here, right? So in the cave, flying in the cave was really focused on using LiDAR odometry, and so. The good thing with LiDAR is it actually gives you, useful measurements straight away, right? While a camera is just a bunch of garbage that needs to be turned into something. And so the amount of power and weight you actually use to turn a camera into something useful is quite a bit, right? Sometimes it can be lighter to just have, and more efficient to just have a LiDAR and reliable, right? So I think there's some interesting questions there as well. But I mean, you have to carry the weight of that sensor, right? So I think that's where a lot of that energy piece comes in. I think something that has the potential to be quite efficient in terms of energy is some of the IMU odometry, right? So I showed this result of running around campus and so on. But part of the exciting part there is that we can do IMU integration for quite a while. And because IM uses only this 6-stop measurement, right? It's a very small space, and you just have a tiny network that does this integration. So I think that's an area I'm quite excited about because it's also not jammable and so on. Yeah.
Another one question. So, many of your work involve lots of different modalities. RGB, you have LiDAR, you have Doppler, radar. I wonder, when you have a model that already works and is been trained with large quantity of data, and now you want to introduce a new modality, what are some general considerations you have?
Right. And I think that is, it's kind of like the thermal is one example, right, where you have this big challenge where, you have, so many visual images compared to this tiny sliver of thermal data. And so that's part of the reason why we're kind of extending this platform, because you can do some things with simulation, but it's tricky to really simulate a lot of these things, right? Like, for example, doing a really good radar simulation in itself is pretty tricky, and doing, so there's a lot of challenges with this. But I think we are seeing that we can exploit kind of a lot of the basics. It's learning on the visual and try and basically just transfer them with smaller data. And that seems to work okay. But yeah, that is part of the reason why visual perception is so popular, because there's so much data, right? And we just don't have that on the other modalities.
Is there any particular theory to make sure whatever was learned before does not get forgotten when introducing new?
Right. So the technique we use here is to just do this alignment, right? So we basically have pixel-aligned visual and thermal data times synchronized together. So we can just say, hey, we want whatever you came up with to look exactly the same. And so that way, you don't actually have to. So that doesn't quite work for LiDAR and radar quite as well, but yeah, that is one trick.
Yeah, I have a system level question because a lot of robotics stack from the lab relies on sub-T stack, which is developed many years ago, and used in a lot of classical method. And now the lab has developed a lot of deep learning based huge model. So what's your thought on how sub-T stack can be adapted in this case? Like how you are going to integrate this model into your sub-T stack, or you can develop this stack?
Right. So I think that some of the things are this RayFronts representation is actually quite similar. It's all new, but it's quite similar to the way the sub-T stack worked. But yeah, I think we're basically kind of overhauling the whole whole stack. Part of it is people graduate, memory gets lost, and and so people don't know what's going on anymore, right? But yeah, I think sometimes we're rediscovering the same ideas again that were in the previous stack. But yeah, I think it's a lot of new things, but we're definitely taking a peek at the stack. Yeah.
Maybe one more question. For the map, you have both geometric and visual input as well. So it's if at all they're misaligned, there's some kind of understanding geometric input, is there more emphasis on vision or have you tested anything?
Yes. So for now, I think this is one of the limitations that we also want to overcome. Is right now it is, if you give it poses, it assumes that those poses are pretty good. So if there's a so it doesn't handle uncertainty, or if you, let's say, give it coarse poses very well, then it's better to just not give it poses. So that's something that we want to change, because it's, for example, if you have GPS or something like this, right, you might want to just give it rough poses to get a coarse scale and align the whole thing. But that doesn't quite work as expected or as we want it right now, because in training it has seen these simulated data sets that are perfectly aligned, And so it doesn't, like we don't model that noise as much.